Welcome guys to my YouTube channel, IB Chemistry with EAF, and today we're going to continue on Unit 2, and we're going to talk today about Structure 1.3, which is going to be Electron Configuration. Okay, so let's begin. So what we will need to know in this unit are things like the emission spectrum. We also need to know the line emission spectrum, the different energy shells, subshells, the ground state, the orbitals. So, and as well how to do the electron configuration, how to write them. Okay, so let's begin. Okay, so the E emission, as we can see over here, is the electrons, they move in energy levels around the nucleus. And this is when they absorb energy, they can move either, or they can move to much higher levels, as we can see in the image. So as you can see, it absorbs, and therefore it goes up, and they can return to a lower energy or to the lower shell by releasing the energy, and the frequency of the emitted energy matches the frequency of the energy which is being absorbed. And an easy way to remember this is we have the absorption, and we can remember that as a jump, so it goes from low to high. And then emission is just you release back, for example, from high to low. So this is going to be low. So from a ground state all the way to the excited state, and then from the excited state all the way back to the ground state. Okay, good. So now let's talk about the energy levels, because there are different levels. So the arrangement of the electrons are also known as the electron configuration. And there is the principle of quantum shells, so it's used as a number. So the lower the number, for example, n equals 1, the closer to the shell to the nucleus, or the shell is to the nucleus. For example, n equals 1, as you can see in the image, is really close to the nucleus. And on the other hand, we have n equals, let's just say 5, and that is much further away. So the bigger the number, the much bigger the shell is, and much further it is, and much more electrons it can as well hold. And there's a specific formula that we can use, which is 2n squared. So the first shell can only hold up to 2 electrons, then the second one can hold up to 8, 18, 34, all so on. And that is important to understand. And as well, there are different subshells. So we have, for example, the different subshells are S, P, D. If you have over 57 electrons, then it also goes to F. But we start at S, which is going to be the smallest, all the way going to P, D, and then F, as we can see. So we have here is 1. So the closest one is going to be 1, and it's going to be S. Then we have, again, the moment it goes up, we can see it goes to S and then to P. And then from there, it goes from S, P, S, and then goes to D. So we can always see it's always increasing. And at one point, after D, after 57 electrons, you're going to hit F. Okay. So what we also need to know is the line emission spectra. Okay, so what we need to know are two definitions. We need to know the continuous spectra and as well the line spectra, and we can see a difference. So this right here would be the continuous, this one, and this one right here is going to be the line spectra. And what's different is that the continuous is a full spectra which is unbroken, and it has all range of colors, so there are no gaps in between. It looks like a rainbow. On the other hand, the line spectra that is made up only of specific and separated lines, and the lines of the color and the lines and the gaps, they show us the color. For example, if you look at the hydrogen spectrum, we can see it begins with violet and ends up with red. And then as well, each of those lines shows and represents a specific energy value. and the lines show the specific energies released when the electrons are dropped between the energy levels. So we can see a big drop shows us it's going from a further shell all the way to a closer shell. For example, from N5, it dropped down to N4, from N4 to N3, 3 to 2, 2 to 1. So, and then what we need to know is if the drop is big, so that means a lot of energy is being released, but it has a short wavelength. So that would be showing us like for the visible range, and we would see the colors of blue and violet. And if it goes all the way down to n equals 1, it's going to be UV light, and that's going to be invisible. On the other hand, we have a small drop, which will give us low energy, but it's going to give us a long wavelength. So it's going to give us, in the visible range, red. But if it again drops, if there's again a very tiny drop, such as from N6 to N5, it could be infrared, and that will be also not visible. So let's look at the image right here. So as I just explained, for example, from N6, so we go over here, N6 would be right here. And it drops all the way down to, oh, I mean here, sorry, all the way down to 5. We can see it's a really tiny drop. And that is literally impossible to see because it's going to be infrared, as you can see right here. And there's a low energy release. On the other hand, let's just say we're going from all the way from N8 all the way down to N equals 1. So we go over here all the way down to N1. We can see it's ultraviolet, so a lot of energy or high energy was released, but it has a short wavelength, and as well, it's UV light, so we cannot see it, it's invisible. Okay, so now let's do some practice questions here. For example, transition from N infinite, so it would be N8 on top, all the way to N3. So what would be the region, and what energy would it be? Okay, so now let's look at it. So we would start from over here, and we're gonna drop all the way down to this. What would that be? So the region is gonna be infrared, and it's all gonna be low because not much energy was being released. So energy, low. And then the region, we can say it was infrared because it literally hit the infrared. So we can do IR. Okay, so now let's go to infinite all the way down to N equals 2. Let's use brown. So we're gonna go from here all the way down to N2. So this is gonna give us what region? It's gonna give us the visible region, and also the energy. It's not low, it's also not a bit too high. It is literally right in the middle, so we can say energy is gonna be middle. And then lastly, N5 to N1. So let's take black. So we're gonna start right over here. We're gonna go all the way down over here. Okay, so that shows us a huge drop, a really huge drop. So that means a lot of energy was released. So we can say energy high. And the region is gonna be, because it went down to U1, and U1 always is ultraviolet, we can say region UV. Sorry. Okay, so now let's look at a one past paper question. So which electron transition in the hydrogen atoms emits visible light? Okay, so let's look at it. So N1, 2, N2. Okay, so if you would go up over here to over here, nothing will happen. Because it goes from, because we are looking here to emit, not to being, as we said, not to be like for the absorption. Because absorption is the one that makes you jump. We're here to talk about emits, which releases. So 1, A is 100% not it. Okay, so N2 to N3, that would be, again, we're gonna start from N2. We're gonna go all the way up to N3. Is that emit? Does it emit? No. It is absorption. It again jumps. We don't care about jumps in this question, because this question asks us about emits. So number 2, or A and B, not it. From N2 to N1, so it'll be right here. Let's do this green. From here to here. Okay, so at least what we can say, there's a drop happening. This time it's not a jump, it's a drop, which is correct. But as we remembered, whatever falls down to N1 is always UV light, and UV light is not visible. So this is also not it. And then lastly, we have N3 to N2. So we'll be right here, dropping all the way down to N2. Okay, so we're right now in the middle of the energies, not too low, not too high. So we're in the Balmer section, and that is exactly what we have, or what we need, because it, one, shows visible light, so we can see it. And secondly, it also emits. It does not absorb. So this is correct. So D is the answer. D. Okay. What we also need to know is the ground state, and that is the most suitable electronic configuration of an atom, which has the lowest amount of energy. This is important to know. Okay. So as I already mentioned before, there were different orbitals. So there were the s orbitals, there were the p orbitals, d orbitals. Those are the ones that we need to know, or what we need to know on how to use them are those three. But what we need to know how to draw is the s orbital and the p orbital. Okay, so the subshells contain one or more atomic orbitals, and each atomic orbital can be occupied by a maximum of 2 electrons. And there are shapes such as S and P. So for example, I already drew the S shape, so it's just a circle. On the other hand, the p orbital is much more complex, because you can draw 3 different ones. You can draw one for pz, py, and then px as well. So let's do this in purple. So we have px right here, and x shows this, x shows us in this direction. So that means, and how we draw a p orbital is by drawing something like an A. So we can go like this. That is how you draw the p orbital. If we would now go to y, okay, so py, how would that look like? That would look like this. So it always shows the direction where it goes. And then lastly, we have pz. Let's do this in brown. That goes up. Okay, so those are the different orbitals that we need to know on how to draw. They might ask you in the exam, can you draw the px orbital? They're gonna give you the specific graph, and then you just have to draw the H shape, or they might ask you for the S shape. Okay, so then we also have the Aufbauprinzip, as I already mentioned before. We start with the S, So we start at 1s, then we go to 2s, then we go to 2p, we go to 3s, 3p, 4s, all of that. As you can see this here. So this is gonna go up like this. I'm gonna go over here. It's gonna go back there, back up there, back over here, 3D, and then only then we go to 4P. So we can see like it's a ladder. It looks like we can all climb all the way up. Okay. So now comes the most important part. How do we write the electron configuration? Okay, this is how the electron configuration is shown. So the electron configuration gives us information about the number of electrons of each shell, subshell, as well orbital of an atom. So for example, if you take the first one, we have the 1s2. And so what the one shows us shows the principal quantum number, while the number 2 on the top, it looks like the squared number, shows us the number of electrons. And then the letter is either S, P, or D, maybe F. And this shows us the subshell. Okay. So there are specific rules that we need to know on how to draw. So there's, for example, in this one, we will see which one is correct to draw and which one isn't. So the electron-filled degenerate orbitals singly first with parallel spins to minimize repulsion. So there are two different, or there's one correct way, and this is the correct way. This one is correct. The other one, please don't do this. You're gonna lose marks. Sorry. And we don't want that. So as it said, we always have to go fill the degenerate orbitals first. So that means we go here one time, here one time, here one time, here one time. But once we're done with that, then we can go on this side. Go down there, down there, down there. That is, and this one we can clearly see is wrong because this one just starts like that. That is not how you're supposed to do it. That is really important to know. That is also the Pauli exclusion principle. So an orbital can hold up to 2 electrons with opposite spinning, which is, yes, this does show opposite spinning, but that does not follow the Hund's rule. And that is important that we follow it. And electrons pair only when no empty orbitals of the same energy is available. So you cannot just, this is really important because this right here, this one, the one in green, could have gone over here to this space. And you cannot do this mistake. That will lead to consequences of losing points. Okay, so how do we draw them? So the boxes represent the orbitals. And the boxes arranged in order of increasing from the lower to higher. So as I already mentioned before, from the closest to the nucleus all the way to the furthest. So we have 1s1 or 1s, which is going to be the closest to nucleus, and then all the way 3d is going to be the furthest. And then the electrons are represented by the opposite arrows of spin of the electrons. So let's do an example. So we do, for example, titanium. And titanium, if you go our periodic table, has an atomic number of 22, which is important to know. So how do we draw it? So hydrogen and helium are in the first group. So we do 1 up. Then we do lithium and beryllium. Then we go from boron all the way to neon. So we do 1, 2, 3, 4, 5, 6. So how many do we have here? We have 6 here. We have 2 over here. And we have 2 over here. So we have 10 right now. Remember, 10. Then we fill up with sodium and magnesium. So we have sodium and magnesium. So we have another 2. Then we go from all the way from aluminium to argon. So we do 1, 2, 3, 4, 5, 6. So we do again a 6 over here. Then we have potassium to calcium, so we do 1 and 2. And then from there we do 1 and 2. So in total we need to have how many electrons? 22. So if you would now count it up, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 18 plus 2 is 20, and then plus 2 is 22. So we have the correct electron configuration. It is correctly drawn as well. There are also shorthands which you can do. So for example, instead of writing the whole full hand, you can also do a shortcut. Instead of writing all the way from here to all the way over here, you can do from 1s all the way to 3p. There's a shortcut where you have to put in brackets Rg, which would be argon, which would be element or numbers or 18. But then you have from there, you will have to do 4s2 and then 3d2. That would be the shorthand version for titanium. What is also important, there are specific rules. For example, the ions form atoms to gain or lose electrons. And then, for example, an anion, which is negative, it's by adding electrons to the outer shell, which is important to remember. And as well, a cation, which is positively charged, so it's, for example, 2 plus, that removes 2 electrons from the outer shell, which is important to know as well. And now that is really important and crucial to understand. There's also the transition metals. For example, you have chromium and copper. And they fill the 4s before the 3d when they're neutral. But when they lose electrons, so if they're a cation, they lose electrons from 4s first, not from the 3d when they form the ions. This is really important. Okay, so let's do another example of how to draw. So for example, we have iron, which has 26 electrons. So we can do 26 electrons. So we do 1s1, 1s2. Okay, so we know we have 6, 2, 2. Then we have other 2. 1, 2, 3, 4, 5, 6. Oh, sorry. So we have 10, 20. Now we need 6 more. 1, 2, 3, 4, 5, 6. There you go. Okay, now, as we can see, we have a cation. If you have cation, what do? We remove 2 electrons. That means we lose. So we would do all of this again. But now we would lose 2. 1. Are we gonna draw? No, because we lose. This is important. So the electron configuration for a neutral iron would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. But now because it is a cation, it loses 2 electrons and it turns to 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. It loses 2. Okay, so now let's go to chromium. This is a bit more challenging. So we're gonna have, because chromium is number 24, but it is a transition metal and it does not fully replace the 4s shell. So we do 1s2, 2s2, 10, 14, 15, 16, 18, 19, just 1. And now we're gonna take the one which is supposed to be here, is gonna go to this one. Yeah? So that means we take this one over here. From here, it goes over here. And then we do 1, 2, 3, 4. 1, 2, 3. No, 1, 2, 3, 4. So the electron configuration is going to be 1s2, 2s2, 2p6, 3s, 2, 3p6, 4s1, 3d5. Okay, that will be the same for copper, but because copper has 29. So if you now count again for chromium, it's gonna have 24 different electrons. So we have 2, 4, 10, 12, 18, 19, 19 plus 5 is 24. Okay, next. So we have copper. This is important as well. It's transition metal. This has 29. So we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Now, same thing as before. The arrow is going to go over here. 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So this is going to give us an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Good. This is something you guys can learn on how to do the full hand and as well the shorthand. So I'm gonna do for you guys the potassium. So potassium is gonna be K, which is gonna be 19. So we do 1s2, 2s2, 3p6, 2p6, 3 S2, so we have already 12, 3p6, and then 4s1. To do with the shortcut, you can do argon 4s1. There you go. That would be the first one. You guys can do the other ones for calcium, gallium, and calcium ion 2+. And then lastly, what we also need to know is the ionization energy from the emission spectrum. This is a bit complicated, so that's why I'm going to take my time. So we have the first ionization energy, so the energy needed to pull one electron off an atom. So that's going to be the first one, as we can see on our periodic table. Table 9, we have the first ionization energy in kilojoules. And if you now look in the graph here, so the big drop tells you that the electron crossed from the one inner shell all the way to the outer shell. So instead of going, so we can see it drop from the S orbital, all the way going to the p orbital, or for the next s orbital. So for example, we have here, there's going to be 1s1, 1s2, and we can see the huge drop, indicating it goes into a new shell. So it's going to be 2s1, 2s2. But because it's not like a big change, this goes to 2p1 and then all the way up. And then until here, we can see it drops again. Okay. So across the period, the ionization energy increases, and this is because of the nuclear charge increases, pulling the electrons much closer to the nucleus, and so the atomic radius decreases, reducing the distance to the outer electrons, and then the shielding stays roughly constant, since electrons are added to the same shell. And as well here we can see there's another version how to draw it. You can see the drops coming in, and drops just indicate that yes, you went from a 1 to a 2 to a 3 to a 4 shell. Good. Okay, now let's do a couple of those questions. You guys can do those questions by yourself, but I will join you for a couple, such as this one. Okay, the table shows the successive ionization energies of the element X in period 2. Okay, so as I already mentioned, what we need to do for this is find where there's a huge gap, and is to find in the period 2, which would be from lithium all the way to neon. That will be period 2. There's one element where we can see this. So now we have to identify where there is a huge gap. Okay, so we can see there's no huge gap, 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 but this is the huge gap. Between 6 and 7, we can see there's a huge gap from 13,000 all the way to 71,000. And that indicates that element 6 is going, or has the transition. And if you now go on our periodic table, the element 6 would be oxygen. So oxygen, or element X, is oxygen. Because we can see the huge drop, which is there. Okay, so now let's try the same thing here. Values for successive ionization energies of an unknown element are. Deduce which group of the periodic table of elements would you expect to find the unknown element? Okay, so to find out this, we would again look for the huge gap. So we have here, this is nothing. This is the huge gap between period 2 and 3. And we always take the one at the bottom, always. So that we know this one is going to be in, or it's going to be in group 2. Okay. Let's look at one more, and then we will dip. Let's look at this one over here. This looks much more complicated. So we have the graph shows the first ionization energies of some consecutive elements. Which statement is correct? Okay, so as we can see the huge drop from here all the way down over here. And this indicates, as like up here, it dropped from a p orbital all the way down to an s orbital, to a new one. For instance, from 3p6, it dropped all the way down to 4s. Okay, so we know this had a huge drop. So let's just say, for example, 3p, and this is going to be 4s. Okay, so y is in group 13? Absolutely not, because group 13 is not the last period, or it's not the last or element in the periodic table. It's going to be, okay, so we can cancel a out. A is out. Is y in group 12? So we have here, there's going to be 1, 2, 3, 4, 5, 6, 7, 8. We know this is going to be 18, 17, 16, 15, and 14. So we can see, is y in group 12? Absolutely not. We can get rid of that as well. Is x in group 12, in 15? No, because in group 15 we will not see such a huge fall from group 18 all the way down to a new subshell, to 4s, for example. So that is also not it. Sorry. So the only answer which is left is gonna be it's gonna be D. X is group 18, which is correct, because we can see from group 18 it has a huge drop. It goes all the way down. Good. So those are the other questions which you guys can look at and answer. Use a periodic table to help you guys out. And I hope this was helpful for you guys. Thank you very much. I appreciate you guys. I hope you have a nice evening. Thank you. Bye.
I need to not pick up my phone. I'll go